How does nuclear fusion work? It all starts with the atom. Atoms are made up of a positive nucleus surrounded by negatively charged electrons. The nucleus is tightly bound and made up of particles called nucleons. These are positive protons and neutral neutrons held together by what's called binding energy. This nuclear binding energy can be released in two different nuclear reaction processes, fission and fusion. Nuclear fission is the process used in power plants. It involves the bombardment of heavy, unstable nuclei such as uranium with smaller particles like neutrons. This causes the heavy atoms to break into smaller fragments, releasing energy and neutrons that can cause more fission reactions. The fragments are often unstable, producing radioactive waste as a result. Nuclear fusion is the opposite of fission. Light nuclei, like hydrogen, are fused together to form heavier atoms. Because more energy is needed to bind two lighter nuclei than one heavier one, the difference in energy is released as a product of the nuclear reaction. A problem with fusion, however, is that in order for nuclei to get close enough to fuse, they need to overcome what's called the Coulomb barrier, or the energy potential produced by repulsive atomic charges. This can be thought of as a sort of atomic gate, where enough energy must be available initially to overcome the potential barrier in order to cause fusion reactions and net energy outputs. This is exactly what happens in the Sun. The extremely high gravitational energy and temperature supply enough initial energy to induce fusion, releasing the heat and light we need to survive. In this fusion reaction, highly ionized hydrogen atoms fuse to produce helium and energy, as well as photons and positrons that can in turn produce extra energy through light and matter-antimatter annihilation. A reaction involving 4 hydrogens releases 24.68 mega-electron volts of energy, or 3.75 times 10 to the negative 15th BTUs. This may not sound like much, but as a whole, counting all the hydrogen, the Sun has the potential to produce roughly 100 to the 40th BTUs, enough to power it for billions of years.